We're starting with chapter 3. As a couple people sent emails to me, there was not a concept coach for set of questions for 3.1. So I removed it from the grade book after they informed me. I appreciate the students letting me know. I wanted to start by just looking over the homework problem that people had the lowest score on. So the problem people had the lowest score on in the last assignment was this one here, problem number 4. And in this problem, we were dealing with the dragster like we did in class, slightly different numbers, but similar problem. So let's just look at this. Read the problem first. I'll read it out loud. I got those kind of mad skills. Some of the fastest dragsters, called top fuel, do not race for more than 300 to 400 meters for safety reasons. Consider such a dragster in this problem starting a race at rest. After the light turns green, the dragster completes a 400-meter race in a time of 7.9 seconds. Now, you will have different times for everybody. What's the first step for me to solve this problem if I'm going to follow the guidelines given in the textbook and that are going to be used on grading? Okay, draw a picture and identify what's been given. So I'm going to draw a picture. My car today is going to be a simple car here. It's going to accelerate at some unknown acceleration. And now let's put the variables we know. So we start at x initial equals, it doesn't tell us where it starts. So I have to make an assumption. What assumption should I make for where it starts? 0, right. Why make life difficult? We'll just say it starts at position 0. Whoops, don't need two equal signs. Starts at position 0. And where does it end? 400 meters. What about the speed? What speed does it start at? Yes. Did I not write? I was pretty close. I just was missing a 4 followed by another 0. Thank you for correction. Come on. 4, 0, 0. There we go. Okay, now to the speed. What was the starting speed? 0. And what was the ending speed? I don't know, right? It didn't ask me for ending speed for part A, but it will for part B. So this is going to be for part B. I need to find it. Acceleration doesn't tell me either. And what's the last thing? Time. What should I put for the starting time? 0, right? Keep life easy. And the ending time, 7.9 seconds. So I have my figure and I have the variables that I'm given. I have the final velocity that's not known. The other thing that's not known I didn't write equals question mark is the acceleration. And so for part A, I'm going to find that acceleration. So I've drawn my diagram. I've identified the knowns and unknowns. I'm ready to get started. So the next step is to think about the concepts at play. But at this point, we only have one concept. What is that? Okay, we have our kinematic equations, the equations that explain how things move. That's our only concept. So my concept is I'm going to use the kinematic equations to solve this problem. So next I have to identify which kinematic equation am I going to use. If I'm going to try to find the acceleration, and I know the starting positions and speed, and I know the ending time, I just use those variables with the kinematic equations to determine which one it is. And since I don't have them listed here, I'll just jump straight to it. The one that is going to let me use the time and those variables to find the acceleration most simply is going to be the one that has all the variables in it. So for part A, I'm going to use the equation x final equals x initial plus v initial t plus 1/2 a t squared. Now, you might recall I said when I'm doing the solutions, I'm going to do the, quote, master problem solver's way of doing it algebraically before I put numbers in, except I put in those zeros first to make it a lot quicker. And so looking at my numbers, I had x initial is 0, and I had V initial is 0. So those terms go away, and I have a fairly simple looking equation, 1/2 AT squared. So solving that for acceleration, it's just algebra. I say just algebra, but a lot of people are going to want to see the algebra, not A, T squared. I divide both sides by 1/2 T squared, so A will be alone and in the numerator position. So looking at what cancels now, the 1/2s cancel here, the T squareds cancel here, and I have A is equal to, remember, dividing by 1/2 is the same as multiplying by 2. So 2x final divided by T squared. And now I'll put in numbers. Now, I guess I do have a calculator here. It's powered by lights, and I have the lights off, so it won't work. So we want to really quickly just get us a number here so we don't feel empty by not getting an answer, especially because it's not the end of the problem.
12.81.
Okay, 12.81. Is that what I said? Okay, I heard somebody say 12.82, somebody say 12.81.
Oh, it's 12.82.
Okay. Now, how many significant digits do I have in this answer? It's actually 2.
Oh, 2.
The 2 there is it's a cardinal number. It has infinite digits. The 7.9 had 2 digits. The 400 is ambiguous. It could be 1, 2, or 3. But in fact, we know these races, they measure it carefully, so it's 3 digits. So the 7.9 seconds was the limiting factor, 2 significant digits. If I was asked for the number, what is the acceleration, I would put 13 meters per second squared because that's the correct significant digits. Of course, if you were asked for the same thing on the homework site, what would you put? Because it calculates that numbers out to 4, I would keep the 12.82 just so I match it as exactly as I can. But on the test, you would want to put 13 because that's actually the correct answer. Right? 12.82 is not the correct answer because you're listing more information than you actually know. Okay, but that's not the end of the problem. That's not what you typed in for your answer, because I had to know the ratio of that to G. So A over G is what we're looking for. And so just divide your number by 9.80, and what do we have? 1.3. And since we're doing this on 1.3 is the actual significant digits, but what are the next 2 for the homework site?
0.8.
0.8. So that means the acceleration can also be written as 1.308 G's. Right? You're pulling 1.3, effectively 1.3 G's with this dragster, which, you think about, that's a pretty, well, of course, a dragster has a pretty good acceleration. So that's the answer to the first part of the question. You would actually type in the 1.308. I just like to write A as 1.308 G's because I like to see that unit there. Any questions about part A? Everybody got that? Okay, then part B is, how fast will it be traveling when it's gone 1.6 kilometers? Approximately 1 mile, right? 1.609 kilometers, but in 1 mile. So now I need to find the speed. What's the easiest way? Divide the distance. Well, I don't know the time for the full trip. It does ask the speed, right? That's actually, double check. Yeah. But yeah, we don't have the total time. We only have the time for the 400 meters. Yes, I think that's Jordan. Divide the distance by 2 times the acceleration. let me write that down. It's not something I've thought about. It's not going to be the easiest, but it might be correct. So that's why I'm looking at it seriously. So you said the distance, so that's going to be, come on, wrong button. That's why. X final minus X initial over 2A. Yes, that is a correct answer, because if you look at your kinematic equations, actually, if you look at your kinematic equations, it's actually not quite that. You have so it's multiplied by, not divided by, and then square rooted. So I could use this. I could say V final squared minus V initial squared is equal to 2A times X final minus X initial. And I can then calculate that way, the V initial 0, X initial is 0. And so we have 2A X final, and then I have to square root it. So that's one way that works. It's a correct way. If you were to do that on the test, it would be perfectly fine because it is a correct way. What I was looking for was actually, I forgot. We don't have the time. I was actually thinking with Mahala there, V is equal to V initial plus AT, but we don't have the time. That is the best way. Good work. Okay, so the V final is the square root to a X final minus 0. Now notice I put in 12.82. I kept 4 digits on that acceleration. Only 2 were significant, but I kept additional digits because I would be throwing away information too early if I truncated and went at that point. So what do we get for this calculation? I'm out of space, so I'm going to squeeze it in over here. Have you for me, Maranatha? You have how much?
202.5.
Okay, 202.5.
Yeah.
Okay, so 0.5 units of meters per second. The problem didn't ask for units of meters per second, though. It asked for miles per hour. So there is one last step because I've run out of space. I'm not sure. I don't want to start a new page. Let's put over. I'm going to have to take this and multiply it by the conversion factor that has meters per second on bottom, so they cancel, and miles per hour on top. So you need to look up that conversion factor. I'm going to stop here and not look up the conversion factor because it's just going to be ugly trying to fit it on this page. I don't want to start a new page for one line.
1.602 though.
Hmm?
There's a mile to the meter.
Well, no, because we need miles per hour.
Right.
So that's going to have the conversion from miles to meters and seconds to hours in it. Okay, so any questions actually about the homework problem at all? Any concerns? Yes,
I have
Cole.
one question. The second half, I think it's the second half of this one is where I ended up getting it wrong, and it was because I didn't use enough digits for them. Is that something you look at and potentially correct, or?
I would look at it. Yeah. Okay. The question for people there at Southwestern was he thinks he got the answer wrong because he didn't have enough digits on the website, and would I consider, looking at it? I would always look at it. Right? It's not going to hurt to say, I think that I had it right and it marked me wrong. Can you look at it? It's never going to hurt. Saying that, it's really forgiving. If you're within 2% of the correct answer, it marks you as correct.
Mm-hmm.
So usually that's not going to be the problem, but it does come up sometimes.
Right. I ended up going out with like a completely wrong answer in the long run because I got down to like the last couple of tries and I was like, all right, I need to try just a different way to do this. And I ended up getting like 0.15. The answer was like 0.07 and 3 other digits. And I think for mine, I had maybe 2 digits.
Well, and another approach instead of, just trying to throw something out there would be send me an email, or if available during office hours, come by my office hours, or, join the Google Hangout. One person joined, but only for like 1 second and then left. So I tried to say hi and she hung up. But I am trying to be available, so especially the students at Southwestern can have some access when they need help with homework. But of course, you too. Okay, moving to the new material. Kind of new because I talked about it in a lecture last week. Now we're going to specifically look at what we're doing in more than one dimension. This last chapter, everything is one-dimensional motion. Well, now we're going to be looking at multiple dimensions because life is in 3 dimensions. We have 3 spatial dimensions and 1 temporal dimension. That is, when we talk about space, we all know, in 3D when you go watch a movie. Well, those 3 dimensions are typically, forward, backward, left and right, and up and down. Forward, backward, that's one direction. Left and right's one direction. Up and down's another direction. Those dimensions have to be mutually perpendicular, or as we like to say using mathematical terms, orthogonal. So the forward, backward is perpendicular to the left, right, and up, down is perpendicular to both forward, backward, and left, right. Or another set you might use is north, south, east, west, and up, down. Right? That's another set of mutually orthogonal directions that you could use. And those are the ones we typically use, one of those 2. Now, there are some other things you may have learned that have interesting aspects. You use things like spherical coordinates, where you have the radial direction, and then you have 2 angles that are perpendicular to that. We won't be getting into that in Physics 151. Physics 251, yes, because, got a little more math fun there. So this picture here is just showing a roller coaster. Went to Worlds of Fun this summer and had fun riding the roller coasters. As luck would have it, when you're a fat man, they actually have fat man seats on the roller coasters. So I was able to ride. Yes, Colton.
You mentioned temporal dimension. What's temporal?
Yeah, time.
Okay.
In physics, you might learn about Minkowski space or something like that. Time is another dimension. We actually take time and multiply by the speed of light to get units of distance. So we have 4 directions that we live in the space-time. That's where the whole space-time, you talk about the space-time continuum. You sound really nerdy. I love to say space-time continuum, but it's a real physics idea. Two-dimensional motion is what we'll start with. Two-dimensional motion means you're only using 2 sets of mutually perpendicular directions. So if you're driving around on the streets of, I don't know where the city is, your motion is pretty much 2 dimensions. You're not hopping up and down, right? You're not changing elevation. So it's just going around the corners and changing with 2 dimensions. So you have to define what your directions are. So in this picture, typically I would just choose to say, well, my directions are going to be like this and like this. Now in my picture, do those look perpendicular? No. But in reality, yeah, they are. So sometimes when you draw your axes, they don't look perpendicular. If you put the little box here, that indicates, yes, that is perpendicular. It's just my perspective makes it so it doesn't seem or look perpendicular. Now, our first of the clicker questions for today, which is available to answer now, is how many confirmed spatial dimensions does our universe have? I add, while you're answering, I'm just going to babble here. I add confirmed because string theory posits additional dimensions of space. But they're not confirmed. So I just didn't want anybody to say, hey, I read Brian Greene's book and you're wrong. It's channel 33 if you're here using a physical clicker. The session ID is web, PHYS. Okay, I'll give it another 7 seconds. And there, I'll stop it. Okay, we had more people answer this time, 57 in total. 0, 1, 34, 19, and 3. Now, I'm not going to ask you to discuss it or draw a card and ask somebody to explain, because this one here is really just a basic knowledge question. There's really no explanation except for, well, they exist. The correct answer here is the one that had the majority, 3 spatial dimensions. There's the 4th dimension, but it's temporal. It's a time dimension rather than space. We can't point a finger in the direction of the time, so it's not spatial. Any questions or complaints or observations? Gila.
Up, down, left, right, forward, down.
Okay, Gila asked, are the spatial dimensions up, down, left, right, forward, backward? Yes.
What about like the
What about what?
diagonal?
Diagonal? Okay, if you have something that's diagonal, okay, let's say here, 2-dimensional. 2 dimensions, I define X and Y. And so if I have a line that's diagonal, that line can always be broken up into a piece that is parallel to the X direction and a piece that is parallel to the Y direction. Okay, redraw it to make it fit. And so it's simply made up of 2 components, 2 pieces, one parallel to one of my directions, one parallel to the other. And that's in fact the goal of what we're going to be working on today, to learn how to discuss these things. Okay, another follow-up clicker question, which of course Gila just answered. What are the traditional definitions for the 3 spatial dimensions? Your options are A or B or C or D. So I know that sounds really ridiculous. What I meant to say is C is both A and B. So don't try to answer multiple answers. Just choose the one that best fits your understanding. Okay, give another 10 seconds here.
Dr. Rudd,
Yeah.
is XYZ also considered the traditional way of looking at that? Or?
XYZ, I think we got even more people answer here. We're up to 60. Sweet mother. All that is good. We have 60 people. I will answer that. That's a good question. Hopefully with. Okay, so there's the breakdown this time. Before I look at the answer, I had a question. What about XYZ? XYZ is a way of us identifying directions. And so I would count XYZ as well, but XYZ doesn't translate into me talking to my mom and say, yeah, I'm going to go this far in the X direction. And so that's why I don't have it listed here. But when we're working with our physics problems, we're going to have to define X, Y, and Z, and then we're going to work within that X, Y, and Z very often. In fact, we will very rarely use, I'm just going to go to the correct answer once again, and not, I pulled out the cards and I was going to draw one, but we will very often think about problems this way. I am not picking up my pen enough. We'll very often think about problems this way, but then we will define an X direction for forward, backward, a Y direction for left, right, and a Z direction for up, down. Because it's quicker to write X, Y, and Z than those words. And when we use north, south, east, west, we'll probably just use NSW, whatever, and keep with that. So the fact is, both of those fit within our traditional sets of coordinates. All right, so this here is a standalone slide. We're going to look at this type of material. I have a demonstration about it in class on Friday. But one of the reasons that's really important to look at this, how things work in multi-dimensions, is when we talk about the motion of an object, like the motion of this ball. So far, I've basically been talking about what happens when I throw the ball up and it comes back down. Will you catch the ball for 13, Megan? Okay. I have to ask because I've had people who just duck and get angry that I threw the ball to them. Of course, I say at them, and that sounds worse. Okay, so if I throw the ball to Megan, it didn't just go up and down. It did go up and down, but it also went horizontally. And what we'll learn is that the motion in the vertical direction can be calculated completely independently of the motion in the horizontal direction. So in the vertical direction, it has an acceleration due to gravity. What direction is that acceleration? Straight down. And it's going to be throughout the entire flight the same value of 9.80 meters per second squared. In the horizontal direction, assuming no air resistance, it has no acceleration in the horizontal direction. So that means no acceleration. What's happening to its speed in that direction? It's in that direction, it's staying constant because there's no acceleration. In the direction going horizontally, no acceleration, constant speed. The vertical direction, as it was going up, its vertical component was slowing down. As it came down, it was speeding back up. Okay. Nice job. No, it's not your fault. I went for my left because that's how we catch with a baseball glove, but yeah. It's been too long since I played baseball, apparently. All right, so that's one of the big reasons we're learning this. So we'll get to that next class period. So for today, going to simple coordinates. This is showing a person taking a trip to go from here, let's call that the dorm, wow, to here, let's call that the store. So you're going to the store, and you have to walk 9 blocks east and 5 blocks north. How far did you have to walk? How far? Okay, Paris tells us 14 blocks because 9 plus 5 is 14. But what was your displacement there? Okay, the hypotenuse. So if I want to find the displacement for this, something has clearly gone wrong with my settings because my pen is supposed to be not that, and well, let's not worry about it. I'll just draw very carefully. The displacement is found using the Pythagorean theorem. So D is equal to the square root of 9 squared plus 5 squared. So 81 plus 25, 106. Square root of 106, well, we know square root of 100 would have been 10. So it's going to be a little bit more than 10 blocks is the actual displacement. Assume I did that right. So that's how we would actually calculate the displacement. What if I also wanted to find the angle that you made here? How would I find this angle? We traditionally use the Greek letter theta there. I would use tangent. I would use, since tangent of theta is equal to the opposite side, 5 blocks, over the adjacent side, 9 blocks, then theta must be equal to arc tangent, which I'm going to write as tangent with a superscript of -1, of 5 over 9. Put that in your calculator. You can use whatever radians or degrees, unless it's asked specifically to tell you the degree, to find the angle. A lot of us are just a lot happier saying, well, I walked a total of 14 blocks. But in physics problems, many times we need to have more detail than that. This is just I've been trying to figure out, I probably spent 10 minutes this morning trying to figure out exactly why or what this path is. It must be a seaplane is what I determined. Because if you were in a sailboat, you can't sail, across Maui. And of course, you couldn't drive your car across the ocean. So it must be a seaplane making stops here. But you have a trip, starts there and ends here. The total distance you travel is a lot bigger than the displacement. And in this case, with all of those different vectors, I'm trying to think of how I can make this work properly, but one vector goes to there, the next one to there, next one to there, next one to there, finally to here. The resultant is found by putting those vectors just as they actually occurred here, head to tail, or tip to tail, or tail to tip. Different people say different words. But you just put the vectors in sequence one after the other, and then the resultant, the total trip, is calculated going from the place you started. So the starting point, excellent, now I can't change pen. There we go. So the starting point was here to the place you ended, so the resultant is that. Now this picture I only have to illustrate how you would map out the trip. I think adding the vectors isn't super difficult, and I've done it before. And so I want to go to, since we only have 20 minutes left here, go to resolving vectors into components, which for students is generally a harder thing than showing how to add the vectors tip to tail or even using the Pythagorean theorem. So here I have, you've done a drawing with your vectors. You added vector A plus vector B and so on. And you came up with a resultant that was 10.3 units at an angle of 29.1 degrees. And you want to know how much of that is in the x direction, how much is in the y. Notice the x and y directions are defined here. If I don't have x and y defined, I really can't tell you how much in the x and how much in the y. But since I do, I know that that can be broken up into two lines. Oh, that is perfect. One line that's horizontal and one line that's vertical. And we call those two lines its components. Now, because our coordinate system has each direction perpendicular, I also know that between those two lines, I have an angle of 90 degrees. So this is a right triangle. For right triangles, our sine and cosine rules are simple, and I'm going to use sine, cosine, and or tangent to find what I'm looking for. So let's say I want to find the x component. I am very concerned about my pen not doing what it's supposed to be doing. In case you are thinking I'm not concerned. I am. If I want to find this x component, I'm going to need to take that vector that has a magnitude of 10.3 and find out how much of it is in the x direction. So I'm looking for the length of this piece right here, and I know the hypotenuse. The total magnitude there is the hypotenuse. How do I know which side is the hypotenuse? Okay, the longest side in a right triangle, or the side that is opposite the 90-degree angle. Either of those will work. But remember, it has to be a right triangle. If it's not a right triangle, you don't have a hypotenuse. So I have the hypotenuse here. Is x the opposite or the adjacent side? Okay, adjacent. How do we know the difference between opposite and adjacent sides in the triangle? Okay. The adjacent side is one of the two sides that's making our angle. The opposite side is the side that's not part of the angle. This is always assuming we're not looking at the 90-degree angle. So the hypotenuse is part of the angle, and then the adjacent side is the other side that's part of the angle. So x is the adjacent side, so I need to look at my trigonometric function that relates the hypotenuse and the adjacent side. And so that's where you look at your definitions for, and I'll just write the correct one, cosine of theta is equal to the adjacent side divided by the hypotenuse. So I can substitute in here the value for the adjacent side is what I'm looking for. So that's going to be equal to my x component divided by, and for the hypotenuse, I'm actually going to put in that number, 10.3. Now, yes, it has units of units, but you know what units means? It means we're just putting some random unit there, and I'm not going to write the random unit. So cosine theta is x over 10.3. Well, I've carefully measured that angle to be 29.1 degrees, so now I just have to solve this for x, which is easily done by multiplying the 10.3 across. So my x component is 10.3 cosine of 29.1 degrees. How would you suppose I find the y component? Jordan?
You did the same concept there.
Same concept, but what's different?
Sine.
It's going to be sine because sine is the opposite side over hypotenuse. So if I want to find the y component, it's still going to be the hypotenuse, but now times sine of 29.1 degrees. Question, Jordan?
I have the numbers if you'd like.
I can't hear you.
That's the number for the actual value. It's 9.00.
For the x then. The reason it's 9.00 is because this is based on the previous problem. And so the y, I'm going to guess, is 5.00, right?
5.01.
Oh, 5.01, round off error. So that's how we can break a vector into its components. Now, when I write that vector, I'm often going to write the vector in terms of its components. So I am going to write the vector as, actually, I pressed a button there. Vector equals 9.00. I can use x with a hat over it. Remember when we talked about that? Or I could use I with a hat over it. I means in the x direction. Plus 5.00 or 01, excuse me. And technically I should put out here units, since it said units. So I have to have that unit there, which is just units. Rather meaningless. So that's how I can write out the vector. Don't need to go through this again, except for to say those two pieces are called the components of the vector. By the way, if I were to go through this, the 10.3, we actually did that calculation back here, the square root of 9 squared plus 5 squared. I just said it's going to be a little bit more than 10. Well, it turned out it was 10.3. Find that angle using the tangent, inverse tangent of 5 over 9 must turn out to be 29.1 degrees. So we've worked the same thing forward and backward. Looking at this picture, if you were asked to add A plus B plus C, what is the answer going to look like in terms of the line you draw for that addition? Okay, it goes from the beginning of A to the end of C. So it's going to go like that. And we call the sum the resultant. I am really getting tired of this pen not working right. I am going to try to choose a pen that's even smaller than the 4 points that I've chosen. Size. And see if it actually will do it. So that's the resultant. I would then, if I did this graphically, I would actually measure the length and the angle. And then from the length and the angle, I would resolve into components. Now, in this case, my angle would be like this. Hey, look, it did make it smaller. Hooray. My angle would be like that. And it's still super sensitive. And then I could use cosine, because that's the adjacent side, to find the x component. I'll bet you this goes back to fat. Yeah, it did. So my x component would be there, and I would just take the resultant times cosine of the angle to find the x component. The y component, now it's going down, so that means it's negative. I'd still use sine there because it's the opposite side. So I think this is our final clicker question, actually. It's open for you to answer now. And the question is, how do you add two vectors graphically? So if I'm going to put them on paper, how do I do this? We'll have practice with this in the homework, of course. Okay, I give it about another 10 seconds. All right, that'll do it. And we have, believe it or not, 1, 1, 1, 1.
They're just too tempting.
You couldn't have answered all of them. You, Colton, probably said, I don't, you do, right?
No, I said B.
You said,
I really, really wanted to say magic.
Okay. So the answer here was very clearly, we use head to tail addition. That is, we draw the first vector starting at the origin, going in whatever direction with whatever length it has. For an exam, for the first exam, you might be required. You'll want to bring a ruler. I have some rulers here in the classroom. You want to bring a ruler and protractor if you have one. Otherwise, I have some that people who don't have them can use. And we'll actually have to show adding vectors, show how it's done. So you'll need to lay them out there with the first one. Maybe that'll fix my pen. The first one starting at the origin, going a distance that's measured to match the length at an angle that's measured to match the prescribed angle. Then at the end of that, you draw your second vector starting at the end of the first that goes the prescribed length at the prescribed angle, and then the resultant. So the head to tail addition method. Subtraction, I said this before, we had this covered in a previous lecture. Subtraction is done just by adding the negative. So if I have a minus b, here's the a vector and the b vector. If I want to do a minus b, the first thing I'm going to do is reverse b. I'm going to say if that's b, then this is minus b. And so if I'm going to do a plus b, I'm going to take my a vector, I'm going to just use the one that's drawn, and at the end of the a vector, I'm going to add negative b. That's my best rendering there of what b looks like, minus b looks like. And so then my resultant is going to go from where I started to where I ended, and I'll measure it out. So if you can add vectors, you can subtract vectors, as long as you paid attention to just what the method is. So there is a carefully done drawing instead of mine. You see, I did go just a little bit below the horizontal line. And of course, when you're doing this on the test, you'd use your ruler, measure the length of your resultant, and then using whatever scale you use, translate that back into whatever the unit was of the problem. And you measure the angle using your protractor. Protractor and compass in my brain mean the same thing, and I know they're very different. I can identify the two things, but I can't tell you which one's name goes with which. Okay, breaking things into components. I've already talked about this in today's lecture because I wanted to with an earlier slide. What I'm going to do here is, oh, look, there's another picture. I'm going to add a slide in between and do something that's different because students often make a mistake. That's not insert. There we go. Insert sesame. The wrong page size, but we'll live with it. So what if I have a vector that goes like this, and I have my x and y directions so there's x and y, and I ask you to find, oh, and I have to give you an angle. So I give you this angle. So I'm going to say the vector A has a magnitude of 10.0 meters, and the angle theta is 30.0 degrees. And I ask you, what are the x and y components of this? Break it down into components. Using the methods that I've already defined, what would you start to do first? Okay, create a triangle. So I'm going to create a triangle that uses that 30-degree angle that I gave you. You don't have to, but I'm going to. So there's my triangle. Now the components must add up to the resultant. So those components have directions. I start at the beginning, and then I go out. So this is going that direction for the x component, or y component, excuse me. So the y component is going up. Is that plus or minus based on my definition of y? Plus. To go from here to the end, I have to go left. So that's my x component. Is that positive or negative? Plus or minus for the x component? It's minus because my x was positive to the right, and that's going to the left. Now I look at this, and for my x component, for that triangle, is the x component the opposite or adjacent side? It's the opposite side because it's opposite to that angle. It's not making up my 30-degree angle. So if it's opposite, that means I'm going to have sine of theta is equal to my x component divided by the hypotenuse. Opposite side over hypotenuse. Solve that for x, and I'm going to have the hypotenuse multiplied by sine of my angle. Now I chose 30 degrees because I don't know about you guys, but when I was in high school, my teacher made us memorize the sines, cosines, and tangents to 30, 45, 60, 90, and so on. And so 30 degrees, I at least had to memorize. I assume a number of you know, sine of 30 degrees is 1/2. And so this is just going to be equal to 5.00 meters for the x component. Now that's the magnitude. Keep in mind, it's going to the left. So when I put my a vector, I have to remember that's to the left. It's in the negative direction. For the y component, the y component obviously can't be opposite. It must be adjacent. So I'm going to have cosine of theta relates the adjacent to the hypotenuse. Solve that for y, and it's a cosine of theta That's a cosine right there. It's a funny spelled cosine. And cosine 0.866, so that's equal to 8.66 meters. And so now if I write my A vector, it's going to be minus 5.00 in the x direction plus 8.66 in the y direction. Better put units on there or I'm going to be wrong. And I'm out of time. Which is